right, good morning, everybody. Welcome to this morning's lecture, where we're going to be talking about departures from ideal flow. Okay. This screen's not working, obviously. Okay, so in the previous lecture, we introduced some key concepts about external flows. Specifically, we were looking at the flows and the forces on objects that arise from pressure and surface friction. So that's what we were looking at. We then met for the first time lift and drag coefficients, which is how engineers talk about lift and drag. We met a brand new flow phenomenon called flow separation, if you remember, where we actually had flow past a sharp corner initially, but then we looked at flow past a cylinder. And this very interesting concept where you have this adverse pressure gradient that trips the flow into the reverse direction. We then looked very quickly at the end of the transition from laminar to turbulent flow inside the boundary layer. So not outside the boundary layer, but inside the boundary layer. We looked at that transition from a laminar turbulent boundary layer to from a laminar boundary layer to a turbulent boundary layer. And we started to look at how that transition affects the actual drag that's experienced on objects. As always, I left you with one final question, which is that it is well known that golf balls travel further because of these dimples, these tiny depressions in the surface of the golf ball. And my question was why? And all of the fluid mechanics that we covered in the last lecture is enough to be able to explain this. So what's the answer? Well, first, let's just remind ourselves of some of that physics that we covered. Okay? So the boundary layer, so that's that flow region right next to the surface, can create flow separation. So we met this case where we've got flow separation past a cylinder, and you've got this low pressure region behind, and this increases the drag. Then we learned about this laminar to turbulent boundary layer transition. So we start off with a thin laminar boundary layer. It then, the flow is so fast that you then get this transition to a turbulent boundary layer, which is much thicker. But the turbulent boundary layer is much better at resisting this flow separation phenomena. Okay, so it's much, much better. So if we look at the drag coefficient for flow past a cylinder, for a laminar boundary layer, okay, we get an early flow separation just here. All right, we get an early flow separation, so we get a larger wake. Okay, the distance across that wake is larger. Whereas for the turbulent boundary layer, it actually delays the flow separation because the turbulent motions here help balance that adverse pressure gradient, so you actually get a narrower wake behind the cylinder or the sphere. So how can we use that knowledge to apply it to a golf ball? Well, first of all, let's consider a smooth sphere. Okay? So here we have the flow is approaching from the left, and here is our laminar boundary layer just there. Okay? And then because it stays laminar, okay, the flow separation happens right there, actually almost on the front surface of the smooth sphere or the smooth ball. So you get this very large wake behind. Okay, so you get a laminar boundary layer, early separation, a large low pressure wake, and hence a larger drag force. With the golf ball, what the changes in the surface do is it creates this transition to the turbulent boundary layer. So the boundary layer exists for far longer before that flow separation finally occurs. And that occurs far later and on the other side of the golf ball. So, and that's all due to the fact that the dimples just change the flow right next to the surface. So we get a laminar to turbulent boundary layer. So here it's laminar, there's transition, here's turbulent. Later separation, we get a smaller, narrower wake, and hence we get a smaller drag force. Hence, when you go, okay, the golf ball goes further. Okay, so that's real application of fluid mechanics. So what are we going to cover today? So that's really a good starting point for departures from ideal flow theory. Okay, so we're going to understand the limitations of what we've done so far. When we were learning about Bernoulli, what are the limitations of Bernoulli? And we're going to understand specifically what happens when flow goes through a hole, okay, when we call that hole an orifice, and we work out how to account for that non-ideal flow. And right at the very end, I'm just going to mention momentum and energy correction factors, because you see that in the textbook white, and I want you to understand where they come from. So let's go back to the Bernoulli equation. So we applied Bernoulli equation at one point to the flow in a large tank, okay? And we looked at what happens when you've got a streamline basically from point 1 all the way through to point 2, where the fluid is exiting at a velocity v2, and here's the height between points 1 and 2, so that's height h. So we assume the flow is steady, we assume the flow is frictionless and incompressible. That's what allowed us to say, okay, we can use the Bernoulli equation here. So if we select z is equal to 0 at point 2, we can say, well, our velocity at point 1 is approximately 0. Our height is at point 1 is h. The pressure is atmospheric at point 2. Our z2 is equal to 0, and our pressure is atmospheric, but we don't know v2. So we apply the Bernoulli equation as we did, must be like 2 or 3 weeks ago now. There's our Bernoulli equation. We can then start to cancel all the terms that are either 0 or equal. Okay, so the pressures cancel because they're both equal to atmospheric. The velocity v1 is equal to 0, which is what we did before. And z2 is equal to 0 because that's where we set our datum point. So we get this very simple expression for the velocity. So gh is equal to half v2 squared. We rearrange it, and v2 is equal to the square root of 2gh. Perhaps with hindsight, now you're seeing this for the second time, you should now be asking, is that really an accurate equation? As engineers, you have to develop this sense of when you get an answer, asking yourself, is that sensible? As an engineer, you have to do that. And so the question here is this accurate? How does it really match up to the real situation if we apply this? So let's take a closer look at what's going on, okay, as fluid goes through a hole or an orifice, as we see here. And there are two really important effects that occur in reality. The first is that friction actually reduces the flow velocity. Okay, and so there are just tiny friction losses here as it comes out of the exit. And sometimes that can be determined by the actual thickness of the stream here. If it's a very narrow stream, then friction is going to be very, very significant. If it's wider and wider and wide, friction is less significant. But the other thing to notice is if you look at these streamlines, as they're coming down or coming into the hole, okay, they don't just suddenly turn at a right angle and go out horizontally. They actually keep on converging, okay? So these streamlines of the flow, they actually keep on converging. So the flow actually narrows. So the true area, okay, of the flow here, the true area of that flow is actually less than the area of the hole. And that area, basically, this phenomenon is called a vena contractor. Okay, so we call it a vena contractor. So these two effects actually change what's going on. Okay, so Bernoulli was great, and it gives us actually a pretty good answer. But sometimes the real situation includes more information that we need to include in our analysis. So these are the two effects we have to remember. So the end effect of this is that it reduces the flow rate through the orifice. So we have to account for that in our analysis. Okay, so the way engineers do that is with something called a discharge coefficient. So these are determined experimentally. So the actual flow rate, okay, so the real one that happens in reality is equal to some factor. This is called CD. This is called the discharge coefficient, some factor times the ideal one. The ideal flow rate is what we get from Bernoulli. But the real one is what we get when we actually take into account all of these losses, the vena contracta and the friction losses just here in this factor here. This is an ideal situation in one sense because we've got the really nice simple analysis of Bernoulli, and then we just apply a simple coefficient to capture these relatively minor effects, but ones which affect our result. So that discharge coefficient generally has a value between 0.6 and 1, right? So it has to be less than 1. And you have to look up that value in tables, or the manufacturer of the device will tell you what the discharge coefficient is. So let's go through this as a worked example, okay? So we've got water flows from a 3 centimeter diameter tube. So here's the hole, or just here, 2 meters below the surface of a large tank. And the question says, assuming no losses, calculate the exit velocity and the volumetric flow rate. So that's the discharge, volumetric flow rate. And B, if a discharge coefficient of CD is equal to 0.6 is applied, now recalculate the discharge. Okay, so that's the question. How do we go and solve it? Well, in the first part A, it says assuming no losses. Okay, so we can use the result from Bernoulli's equation that we derived to calculate the exit velocity. If we know the exit velocity, we can calculate the volumetric flow rate, or the discharge. So the velocity at point 2 is equal to the square root of 2gh. We have all of our quantities already known. So v2, we substitute in our values, it ends up being 6.26 meters per second. And the flow rate is equal to the area times the velocity. So the area here is going to be pi d2 squared upon 4. So here's pi d2 squared upon 4 times the velocity v2. We substitute in our values here, and we end up with a velocity, discharge of 4.43 liters per second. So that's the flow rate. So that's part A. Now if we go and do this with the discharge coefficient, which is what we're told to in part B, the discharge coefficient is 0.6. So we just multiply the answer we got from part A by 0.6. So here's 0.6 times our answer, we end up with 2.66 liters per second. So that's our actual flow rate, because we've actually got quite a low discharge coefficient there. Okay. We can also then go and work out what the actual velocity is from that, and that, of course, is the actual flow rate over the area at point 2, which would be 3.76 meters per second. Yeah?
So, while finding the actual velocity, shouldn't the area be the area of the conveyor?
The vena contracta, yes, but you're not given that information here. Yeah, good question. So the question was, should the actual area here being used be the area of the vena contracta? The answer is strictly yes, the area should be. But we're not given any information about that, so we have to assume that the area is the same as the outlet area. All right, so I've introduced this idea of what happens to the physics of flow through an orifice, okay, and so here is the piazza pole for today. So fluid flows along a pipe through a sudden short contraction known as an orifice, okay. You've got two options here for the flow pattern. In both cases, you can see we've got flow separation, okay, off the corner here. But which one is it correct? Is flow pattern A correct, where everything comes through like this, or is flow pattern B correct, where you get a little change in the geometry? Here you can see we've got recirculation regions. So that's your piazza pole for today, and it should already be open for you. Okay, let's see how you guys are voting. Okay, so 83% of you think it is option B, which is very good because it means you've been understanding what we've been going through in the lecture. So why is it option B? It's for the very same reason that we had the vena contracta for the flow out of the tank. Okay, the flow entering the orifice cannot turn immediately. So if you've got flow coming down here very close to the front wall, it can't just turn immediately at a right angle. It's got momentum, and so that momentum keeps it going. And that's why you get this vena contracta area just here. So that's good. So you've understood how the real flow is. Okay, so this brings me to an orifice meter, which is a very commonly used way of measuring the flow. And it's a rather extreme variant or version of the Venturi meter that we met earlier in the course. And basically, it's looking at how to measure the velocity by looking at the pressure difference across the orifice. So the one thing to remember here is that measurements have shown, very careful measurements have shown, that actually the pressure here is more or less constant across this eddy, this recirculation region that we have here, through the vena contracta and then back into the eddy on the other side. So the pressure is more or less equal. So that means that we can measure the pressure here on the wall with the pressure tapping, and we can measure the pressure here. The advantages of this type of device is that it is cheap, it is small. However, it does dissipate a lot of energy. So if you're looking to measure something without losing energy, this is not your option. However, if you are not worried about that, this is a really good way of measuring things, and you'll find it everywhere. So how do we analyze this? Well, let's just look at a slightly more complex picture of it. We've got the same situation that we had before. We've got the oncoming flow here at point 1. Here is the orifice plate, just here. Here you can see we've got the vena contracta as the flow converges as it goes through that region. We've got our recirculation regions either side. And then we've got our manometer tube attached either side of the orifice plate in order to measure the pressure difference. So that's delta P, okay? So that's the pressure drop across the orifice. So we're now just going to use Bernoulli to analyze this because it's appropriate at this point. So here is the Bernoulli equation, and we can then start to remove some terms that are not useful. For example, along the center line, where we're going to be measuring everything, the Z location is equal. Okay, so Z1 is equal to Z2. So that reduces the equation to a simpler version. Now we're just going to do a bit of algebraic rearrangement because we can see we want to get this in terms of the pressure drop. So P1 minus P2 here. So P1 minus P2 over rho gives us a half V2 squared minus V1 squared. Hopefully this is familiar to you now a little bit because it's very similar to the Venturi flume that we did 2 or 3 weeks ago. So now we arrange for V2 squared minus V1 squared. And P1 minus P2 is equal to that pressure drop, delta P. And then we use our knowledge of the mass flow rate. We can't go any further with that equation, so now we use our knowledge of the mass flow rate. So the mass flow rate at 1 must equal the mass flow rate at 2 because we are conserving mass. So M1 dot is equal to M2 dot. So that's our mass flow rate. Well, this is rho A1 times V1 is equal to rho A2 times V2. We rearrange that equation to get an expression for V2. So V2 is equal to the ratio of the areas A1 over A2 times V1. That means we can substitute into our expression for here, we can substitute in for a V1, and so V1 gets substituted in here. After a little bit of algebraic manipulation, we have that V1 squared into A1 squared over A2 squared minus 1 is equal to 2 delta P upon rho. So still quite simple, to be honest, quite a simple equation. We're just going to rearrange that one more time in order to get a nice expression for the velocity, V1, in terms of the pressure drop across the orifice. So I'm just doing a bit of manipulation. I'm just rearranging this equation here. I'm dividing through. I'm taking this onto the right-hand side. Finally, my flow rate is equal to A1 times V1. Okay, and you can see now I have an expression for the flow rate and also for the velocity in terms of the square root of delta P. This is the main thing. All the other things, this is basically geometric and this is a state property. So what we have here at the end of all of that analysis of Bernoulli is a flow rate Q is equal basically to a constant times the square root of the pressure drop. So quite a nice simple relationship. We just have to work out what that constant is. And you can see that the constant obviously depends upon the area and the density of the fluid being measured. So at this point, we might say, okay, what area, so a bit like the worked example we just did, what area should we use for point 2? Because that's where we've got the vena contracta. Well, that vena contracta area here, that turns out to be quite difficult to actually know, quite difficult to measure. Because it should be, the area should be pi times dv squared upon 4, where dv is this diameter here, the diameter of the vena contracta. So this is why a calibrated discharge coefficient becomes super useful for you as an engineer. So if we replace that area, AV, by the area of the orifice, so pi d naught squared upon 4, because we can measure that distance there between either side of the plate. The way we do that is with our discharge coefficient. So on the left here we had, this is the area of the vena contracta, which we don't know. Here we've got the area of the orifice, which we do know. And then we take into account that reduction of the area using this discharge coefficient here of CD. We can then run experiments in order to identify what that value of CD should be. Okay, so let's continue on this discussion of real geometries. And we've got key elements, which include pipes, they include valves, include plants and turns. You can see this is a bend just in the pipe. This is a sudden expansion. Now, as engineers, when we are looking at all these sort of systems and real flows, what we divide the losses that we need to account for, these are the friction and the energy losses, into two major groups. And these are the major losses and the minor losses. So these are what we want to know. So how do we do that? How do we get the major and the minor losses? So the major loss, especially when you've got maybe a long geometry or a long pipe, okay, is going to be friction. That is going to be the major loss of energy. So you've got friction along the wall of the pipe. You might have the interruption of the smooth flow caused by a fitting like this. Of course, this gives flow separation and everything that we saw earlier. So we've already looked at how to determine the energy loss or the head loss for a pipe. Okay, we did that last week, and we derived this equation where we got this friction factor. So for most fluid problems, okay, the experimental results have to be used to identify that. But if it's laminar, it tends to be easier. In terms of the minor losses, so the major losses are generally friction related. The minor losses are due to change in shape. because they happen only at a very localized area. So here you've got a loss as you go to a sudden expansion or a sudden contraction. You might have inlets and outlets. You've got bends and branches and valves. So these are very local. Okay, so they might just happen at one part of your system. But friction loss might be all the way along the pipe, and that's why it's so much larger, because they're present for a much larger area. So in a typical system, these are called minor losses since they're much smaller, but we still need to take account of them if we want to actually do our engineering accurately. How do we take account of the minor losses? This is where we now use loss coefficients, and we can include these in the steady flow energy equation which we derived. So if we consider this, we've got a valve here as an example. We've got 0.1 on the left and 0.2 on the right, and here's our mean velocity coming in, um. And we use a loss coefficient which relates to the pressure difference. So here is a loss coefficient. So this is a dimensionless coefficient, KL, and that's equal to the pressure drop across this very complex geometry divided through by a pressure, which is a reference pressure of the mean flow. So that's a half rho squared. And that is our loss coefficient, and I'm now going to show you how we include that in the steady flow energy equation. That loss coefficient can be determined by measuring the pressure drop. You can see this loss coefficient will change depending upon the flow, because if the flow changes, the pressure drop changes, and hence the loss coefficient changes. This is a simplified form you might find for other changes in what we have, that loss coefficient is actually a more complex expression. But in its most simple form, this is how we use it. So we can include this as a head loss or an energy loss. A head loss means energy loss, just expressed in terms of meters, inside our steady flow energy equation by saying, okay, here is the head loss due to this minor friction, this minor effect, sorry, not minor friction, just minor effect. So here's my energy loss coefficient times squared upon 2g. For different shapes, these loss coefficients have different values. So you might find for a sharp edged inlet that it's 0.5, but for a very well-rounded inlet, it's very small, so you get very little loss, so it's 0.03, one order of magnitude smaller. When you've got a sudden expansion like this, your loss coefficient tends to take this form, okay, and we can plot it like this, and here you can see that as the ratio of the diameters change, the value of that loss coefficient also changes. So you need to be able to know what your loss coefficient is. I saw a hand up over here, yes?
Wait, so for is the initial velocity before the flow meets the sharp edge?
Yeah.
The inlet?
Yeah, it's the mean velocity before you meet the change in the geometry. Okay, so how do we use a loss coefficient? I said that loss coefficient goes into the head loss or the energy loss. So let's just consider an example here. Here we've got that flow in the tank again, so here's the streamline, but now you've got this sharp-edged inlet here, so here's the loss coefficient of 0.5. So it's very clear, because we're told we have a loss coefficient, that we can't use Bernoulli here, because Bernoulli is frictionless, it's incompressible and steady. So we've got friction losses now at that pipe inlet. So this is how we will include it in the steady flow energy equation. Here's our steady flow energy equation with all the terms. So here's our P1 over rho g plus V1 squared over 2g plus Z1 on the left. We've got the same on the right. Here's the pump, the useful pump head. Here's the turbine head. And here are the losses here. And this is where we will include the head loss coefficient. So that's where we use it. So the head loss, or the energy loss due to a change of geometry like that, like this, sharp edge inlet, gets included just here. Okay? So this is how we include it on an individual basis. But you might imagine that actually your engineering system that's pumping, it could be cooling fluid around your engine, it could be all sorts of things, it is more complicated than that. We might have a rather complex network. So at this point, we can say, well, I know I've got minor losses and I've got major losses. Okay, so here are my major losses. So this is the major energy loss, and as you can see, this is the friction-based energy loss. And then I've got my minor losses, so these are the ones due to the changes in geometry at each of these network points. So as I've said, those energy loss coefficients can be found in basically data books or tables that will generally be provided for you. It's very rare that you would have to measure it or work it out. So I'm just putting that there just so that you know how we do this more generally. So how do we include this in an example? So we've got a Parkes water feature is supplied with water from a large tank, okay, via a uniform pipe of length 35 meters but diameter 150 millimeters. So it's much, much longer than the diameter. Immediately your brain will be thinking, there's going to be friction losses along the long length of that pipe. There is a free discharge point 10 meters below the water level of the tank. So here's 10 meters. Here's the free discharge point just here. Find out how long it takes to deliver 2,000 liters of water. In case A, assuming no losses, and in case B, allowing for an entry loss coefficient, KL of 0.6, and a pipe friction factor of 0.05 F. So this is a really good way to compare how to include losses and how to neglect losses. So in part A, we're assuming no losses. The flow is incompressible and it's steady. To estimate the time that we need to deliver 2,000 liters, which is what the question asks for, we need to know the flow rate, the volumetric flow rate. So that's Q, which is equal to the area at point 2 times the velocity at point 2. From Bernoulli, from our lossless analysis, we know that the velocity must be equal to the square root of 2gh. We put in the value for h here, which is 10 meters, and we get a velocity of 14.01 meters per second. Our flow rate is equal to the area times the velocity. So that's pi d2 squared upon 4 times v2. And we get a flow rate of 0.2475 meters cubed per second. The time then to deliver the 2,000 liters is just given by the total volume that we want divided through by that flow rate. So 2,000 divided through by our flow rate Q, which is 0.2475, and we end up with 8,080 seconds. So that's assuming no losses. And basically, because there were no losses, we know we can apply Bernoulli. But if there are losses, then we have to actually take those into account, which is in part B of the question. So we have an entry loss coefficient of 0.6, and we have a pipe friction factor of 0.05. So the flow is fully developed. It will be because the pipe is so much longer than the diameter. We know we can't use Bernoulli equation, so we must use the steady flow energy equation. So here is our steady flow energy equation. Now we can start to enter some of the values that we know. Okay, so P1 is equal to P2 is equal to P atmosphere, okay, because it's open to the atmosphere. There is no pump and there is no turbine, so there are no energy losses or head losses due to a pump or a turbine, so those are equal to 0. This then reduces the equation to a far simpler one. So the value of Z1 is equal to H. So here's H, and that must be equal to V2 squared over 2G plus the head loss, or the losses due to major and minor losses. So now we need to find the velocity V2 in order to find the flow rate Q. But to do that, we need to know the head losses, okay, or the energy losses in the system. So we have a loss coefficient of 0.6 and a friction factor of 0.05. We have two contributions to that energy loss, or the head loss. We've got pipe entry, and we have friction. Okay? So we can say that this term, HL, the head loss, is equal to the head loss of pipe entry plus the head loss of pipe friction. So we're going to combine those two together, just as we saw for that pipe network, except we've only got one term in that summation. So for the pipe entry, well, the head loss due to pipe entry, or the energy loss, is equal to the loss coefficient KL times UM squared upon 2G. And for pipe friction, we know that the pressure drop from our derivation last week is equal to F times L upon D, where L is the length, times a half rho UM squared. If you remember, we can relate the head loss due to pipe friction to the pressure drop over rho G. So this allows us to say, well, that my head loss is equal to the friction factor times L upon D times V squared upon 2G, or UM squared, sorry. And we know that for both cases, we need the flow velocity in the pipe, which in this case is going to be V2. And that's the critical, important velocity to use in this example. So now we just have to go and substitute these expressions for the pipe entry and the pipe friction into our equation here, and we basically complete the problem. So our energy equation therefore becomes H is equal to V2 squared upon 2G plus the pipe entry head loss and the pipe friction head loss. We substitute in our terms, and then we've got our loss coefficient times V2 squared upon 2G plus this FL upon D. And if we therefore just do a little bit of factorization, we have that that's equal to V2 squared upon 2G into 1 plus KL plus FL upon D. We know all of those terms now except V2, so we can work it out. So our expression for V2, when we rearrange that equation, is equal to the square root of all that lot. We put in our quantities, which we now know, and we end up with a velocity of 3.85 meters per second. So finally, we can work out what the real time to deliver 2,000 liters is, which should give us this value here, 29,000. Yes,
why did you convert meters into meters cubed there?
It should be 2 meters. 2,000 meters.
Oh, I think you might be right. Do you think he deserves some Swiss chocolate? Yes, I think he does. I think he does.
What was the mistake?
Hmm?
What was the mistake?
Oh, too late. Too late.
I want to know this mistake.
No, so he's right. So this should be 2,000. This is 2,000 liters, and it should be. You should need to convert that to meters cubed. Yeah, which will make a difference to this result. Okay. All right, I will correct the notes online. Thank you for that. Okay, so the last thing I just want to cover is this, how we account for momentum and energy in our equations. So, in fact, when we considered Bernoulli in the pipe, we actually assumed we had a uniform velocity. The reality is that we know we've got fully developed flow. And the way that we take this into account is with momentum and energy coefficients. So the momentum coefficient just considers what is the momentum flux and the mass flux, which is equal to, so you've got these two multiplied together. So our momentum flux is equal to rho AV times V. Now, if the velocity is not uniform, we have to do that over little elements across the diameter of the pipe, so we end up summing up our mass flux times velocity times the area. This is inconvenient. We don't want to do that. So we have a good idea what the average velocity is, and so we use a correction factor beta for that. And that correction factor depends upon the flow regime that you're in. This is what you'll see in the textbook white. We do something very similar for the energy. So there's an energy correction coefficient. If you look here at the bottom, you'll see it appears in the white version of the steady flow energy equation. Well, where does this alpha come from? So this comes from considering the kinetic energy flow past a point. Okay, so we've got a flux here. Here's our energy, and so we end up with a half rho AV cubed. This is the local term, but we want to know what the actual average flow of energy is. And so this alpha coefficient is used. I don't go into this in any great detail because it's a minor detail, but people get confused if they see it in the textbook and say, where did that come from? I'm much more concerned that you understand the concepts. So this is just an explanation of where it comes from in the textbook. So my end of lecture question. In this course, we have looked at flows in internal geometries and external flows around objects. And you can see we had fully developed laminar flow in a pipe. However, we don't always have a situation like that. What would happen, in fact, if this pipe here is only partially full? What happens to the velocity profile for a partially full pipe? Or what happens if there's no top boundary at all? What happens to this velocity profile? Okay, so that is your question to think about. In this lecture, we've looked at the differences between ideal and real flows. We looked at flow through an orifice, and we met this vena contracta. We learned how to use discharge coefficients and how loss coefficients are used to account for sudden changes in geometry. And I left you with one final question. At this point, I'd like to thank everybody who's wearing a mask, and I'll see you next week on Monday.